Hello everyone, welcome to the best project video where I'll be sharing an intriguing experiment that blends physics, sounds and beauty of mathematics. We'll explore how sound waves interact with a natural vibrating system to create captivating visual patterns known as Lissajous figures. Let's introduce our experiment. The experiment focuses on understanding sound wave dynamics using an elastic membrane. This membrane is attached to a speaker and a small reflective silicon wafer on it is mounted at the center of this wafer, at the center of the membrane. When sound waves are transmitted, the membrane oscillates in response and producing patterns that combine transverse and longitudinal waves. These vibrations are captured by reflecting a laser beam of the silicon wafer, projecting the resulting motion onto a flat surface. What's the significance of Lissajous figure? These patterns, known as Lissajous figures, provide a visual representation of the interactions between two harmonic oscillations between two different frequencies actually. One along the horizontal axis, another along the vertical axis. By adjusting the sound frequencies, phase differences and amplitude ratios, the experiment generates complex symmetrical and dynamic patterns. You can see our experimental setup here. For the setup we used a laser pointer, an elastic membrane, a balloon, a speaker and amplifier, a silicon wafer and a frequency generator. A laser beam reflects off the wafer, creating a visual patterns that change as the sound waves alter the membrane's vibration. This configuration enabled us to observe both monophonic, single frequency and biphonic sound waves. With monophonic sound waves, the patterns range from circles to ellipses, depending on frequency ratios and phase differences. At the natural frequency of the membrane, which changed, but we found it around 448 Hz, we observed a perfect circular pattern indicative of resonance. And biphonic waves introduced even more complexity, generating dynamic figures due to inharmonic frequency ratios. For instance, frequencies related by a 3:4 ratio produced and 1:2 and created stable and symmetrical shapes. This experiment demonstrates the intersection of wave mechanics and visual representation with applications in acoustics, signal processing, and even art. At the heart of this experiment lies the principle of normal modes and Lissajous figures. Normal modes describe the natural vibration patterns of the membrane, which depend on its shape and frequency, as you can see here. Lissajous figures are the visual patterns created when two perpendicular harmonic oscillation interacts. By adjusting the frequency ratios, amplitude and the phase difference of the sound waves, we can precisely control these patterns, revealing the elegant connection between wave mechanics and geometry. This interplay forms the foundation of our experiment, and this is the theory part. And as you see here, we use the Python code for the error of the width of the 1:1 ratio frequency. And as you can observe that our error is very low due to the usage of precise instruments. Thank you for taking time to explore this fascinating experiment with me. I hope it offered you new insights into the beauty of wave mechanics and sound dynamics. Feel free to reflect on these concepts, and until next time, stay curious and keep learning. Thank you.